all so much for the very generous invitation and that overly generous introduction. I'm so excited to be here today to share with you a little bit about tourmaline. And you might say, why tourmaline? Well, hopefully by the end of the presentation that will become clear. So we'll just look at some of the many faces of tourmaline. So many of you know tourmaline because it occurs in museums worldwide. It makes, including your very own Rice Museum. It forms these lustrous crystal clusters that are sought after by collectors as well as interior designers. And many of these crystals are so transparent that, of course, we can cut gemstones out of them. So many of you might be familiar with the gems of tourmaline. Tourmaline occurs in an unrivaled spectrum of colors from black to white, and three of the colors are shown here. This is this beautiful pale pink with a gemstone, these lustrous vivid chromium greens, or these vivid neon blues. And these are all cut from very large, completely transparent crystals, unrivaled by many other minerals. Now, these minerals, you might say, well, they're minerals, so they should contain information. And in fact, gemstones do contain some geologic information. But it's the more typical tourmaline, like these, that contain much more scientific, valuable information. So these are the kinds of tourmalines that I work on. Not quite so large. Here they're 20 microns, and here they're about 100. But they're filled with chemical fingerprints, and you can see some of the color zones shown in this mineral here. So today I'm going to focus on these more typical tourmalines. So after a brief introduction to the mineral group of tourmaline, then I'm going to give you three examples as to how we can use tourmaline to extract the geologic evolution of the rocks in which they occur. So the first example will be using tourmaline as a geologic thermometer. The second example will be using tourmaline as a host rock, a provenance indicator. So where did the rocks come from? And the third will be as a paleofluid composition recorder. So as the fluids penetrate the rock, tourmaline can record some of that information. And this is a very famous tourmaline specimen shown here. It's called the bicolored steel. It has this beautiful watermelon coloring from pink through colorless to green, pencil-shaped crystals, and this was sold for about $1 million 10 years ago. I can no longer afford to collect. So this is to brighten your day. But thank you. But don't worry, there's only one slide like this, and I just want to give you three takeaways from this slide. So the attributes that allow tourmaline to be such an exemplary recorder of its geologic environment are its structure, with two fragments shown here, and its chemical composition. So this chemical composition is shown here by this very long chemical formula with some generic letters in it. And each of these generic letters corresponds to a specific site in the crystal. And each of these sites are slightly different in size and allow different elements to be included. Now, what's important about the chemical formula of tourmaline is only one thing. It requires boron to form. So whenever you see boron or tourmaline in a rock, you know there's been boron. So it's boron, it's the Earth's boron recorder for the crust. Now, these two structures here, so all crystal structures are made of polyhedra of different sizes and shapes that come together, and several of those are shown here. This is in plan view, and this is in cross-section. And crystallographers use this very clever coordinate system, A, B, and C, to define the organization of the tourmaline structure. So if we look down on the structure, you'll see this ring of tetrahedra the bases are all pointing up and the tips are all pointing down. So again, in cross-section and in plain view. So within these small tetrahedra is a silicon, and then the silicon is surrounded by oxygens. Okay, this is going to become important later. So that's what you need to remember. So these silica tetrahedra all point in one direction, and the plus C direction is going this way to the top of the base. Okay, we're going to come back to plus C. Now, all of these different sizes of polyhedra allow nearly the entire periodic table to be incorporated into the tourmaline crystal. It needs boron, but it can take in anything from hydrogen all the way to bismuth and just about everything in between. So that's what all this is. Well, this tourmaline compositional complexity has long been known. In fact, John Ruskin described tourmaline's composition as closer to the making of a medieval's doctor's prescription than the making of a respectable mineral. And this was in 1891 in his very famous book, The Ethics of Dust, 10 Lectures to Little Housewives on the Elements of Crystallization. My students gave me a copy of this book. The compositions are so prolific, as Julian mentioned, of tourmaline, that it's not just a group, it is a supergroup. And it now has about 43 recognized individual species that exist. Some of those that you may have heard of are schorl, which is a sodium iron tourmaline, dravite, which is a sodium magnesium, and elbaite that makes these beautiful clear gemmy crystals is a lithium aluminum tourmaline. And this broad chemical opportunity for tourmaline is what allows it to encode so much information. So this wide chemical promiscuity, so to say, allows it to be stable in pressure temperature space over nearly the entire Earth's crust and upper mantle. So it forms at very low temperatures of about 150 degrees, and that's shown here by these little splays of tourmaline that are from a geothermal field in Indonesia. It forms throughout the crust and into the upper mantle. And this is a tourmaline that actually has diamond inclusions. So it occurs together with diamond at about 200 kilometers depth and about 1,000 degrees C. So it really doesn't care what temperature pressure regime it has, it just needs boron. So it forms in all types of rocks, including near ore deposits, and Clark bought some beautiful breccia up here of tourmaline. It's kind of black, but it's potentially an ore deposit indicator. It occurs in all types of igneous rocks, which we see those big beautiful crystals form in pegmatites, but also in granites, and even some kimberlites that are eruptions from the mantle. It forms in a variety of metamorphic rocks, those that have been those that have been reheated and metamorphosed from another source rock. And it even forms in sedimentary rocks. And for those of you who like gravels or sand, this has to be some of the most beautiful gravel or sand I've ever seen from Vietnam, which has tourmaline, spinel, and ruby. So that's quite the clastic sediments. So this flexible chemistry will record each of these different environmental conditions. And it's also mechanically and chemically stable. It doesn't weather, as you can see in the weathering cycle, because it just is tough. So tourmaline has staying power, as we just described. Tourmaline has formed throughout much of Earth's history also. The oldest known tourmalines, some of those are shown here. They're from the Issawa the Issawa complex in Greenland. They're dated at about 3.8 billion years. And some people have even proposed that tourmaline could have acted as a substrate for early life. And I'll show you why in a little bit. Two other very ancient terrains that contain tourmaline. One is shown here. This is the Beartooth Mountains just next door in Montana. These are 2.8 billion year old dravites. These are the green minerals here. And even those occur in the Jack Hills, the area in Australia that's known for its very old zircons. These are about 2.6 billion year old tourmalines that are in those rocks. And tourmaline is still forming today. We see it in geothermal systems. In the geysers field in California has tourmalines in them, and also in the Larderello field in Italy. Two of the most prolific geothermal systems in the world have tourmaline in the rocks. Now, we have to work really hard in Louisiana to find minerals. And sometimes we even have to go to the Gulf of Mexico. And if we work hard enough, we have found tourmalines very small, this is a 20 micron scale, in the cap rock of a salt dome that's actively forming down here in the Gulf of Mexico. So these are forming very recently at the Challenger Knoll area in the Gulf of Mexico. So now we have one additional attribute that's needed to describe why tourmaline is such a useful and unique recorder of the environmental signature. And that comes back to its structure. Now remember, plus C, okay. If we look at the morphology of a well-formed tourmaline, we see that it's asymmetric. The top doesn't look like the bottom. And we call these two ends of the crystal poles. So the plus C pole always has more crystal faces, and it's steeper, it has steeper crystal faces, and the bottom is flatter and has fewer crystal faces. So by the end of this talk, you're all going to be crystallographers, and you're all going to know plus C on a tourmaline crystal when you see it. And why is that? Well, it goes back to its structure. So if we turn that fragment of structure on its side, with the plus C pointing in this direction, we have our ring of silica tetrahedra that are all pointing in the same direction. So again, it's not symmetric. That causes a slight net negative charge at the base of the polyhedra, and so the crystal forms differently. This asymmetry to the tourmaline has led to two very important technological properties. Tourmaline is both pyroelectric, meaning it develops a charge, a differential charge at each end of the crystal with heating, and it's also piezoelectric, meaning it develops a charge, a differential charge with pressure. And the pyroelectricity is demonstrated over here by this crystal. This was a tourmaline crystal that was cooled to minus 170 degrees and then warmed in humid air. It crystallized ice, and you can see there's more ice crystals on this side of the tourmaline than on that side. So we all know that this is plus C. So tourmaline has this very important electrical property to it. It also was used during World War II as a pressure gauge to monitor underwater explosions. And today, some compositions of tourmaline are also used to monitor underground nuclear explosions. So it's become very important technologically. And this asymmetry also allows the mineral to selectively incorporate different chemical elements at different ends of the crystal. And that will become important a bit later. So tourmaline's intrigue started a very long time ago. In the 1700s, the Dutch traders realized that tourmaline would pull ashes from their meerschaum pipes. And about 40 years later, Carl von Linnaeus, who you know from naming fame in the biological world, made the initial link between pyroelectricity and the ability to pull ashes from these pipes. And he named it lapis electricus, kind of cool. The name didn't stick, but he recognized the importance of these electrical properties. And about 10 years later, this gentleman here, Aponeus, performed some of the first experiments on the electrical properties of tourmaline, and he demonstrated that, in fact, it became electrified by being warmed, and that opposite ends of the crystal developed opposite charges. And this was then used a few years later by Ben Franklin to underscore and support his theory of electricity, of both positive and negative electricity. And then, of course, tourmaline was forgotten for another few centuries, and the crystal structure was solved in the 1950s, and then we had an explanation as to why it had these somewhat unusual electrical properties. So tourmaline's attributes just make it a phenomenal geologic recorder. It has very complex chemistry that systematically responds to the geological environment in which it forms. It encodes this information over very small scales, as you can see by this intricately zoned tourmaline crystal. So it's basically a mineralogical witness to its geological environment. It also has this very flexible structure, meaning it can take in the entire periodic table, and it's durable and recalcitrant such that once that information is encoded, it doesn't disappear. So it retains this history through geologic time, even through our 4 billion years of Earth's history. So tourmaline is a really unique recorder of its geologic event. So now we have to just develop the precise readers so we can understand all the chemical information that's stored in this remarkable vessel. So here I'm going to just briefly give you 3 examples of how we've used or decoded the information stored in tourmaline. The first is as a thermometer to extract the thermal history of terrains. The second is to interpret the growth of the continental crust. And the third is to extract transient fluid compositions that can be embedded in tourmaline. And in fact, these are small fibers of tourmaline here, little blonde fibers. Okay. So during metamorphism, and again, metamorphic rocks are pre-existing rocks that get heated, and usually heated and subjected to some pressure, there's usually detrital tourmaline in those rocks. And with heating during metamorphism, tourmaline will begin to grow and it will grow on a pre-existing detrital core. And we can all see plus C, right? Nod, it's like students, yeah. Okay, we can see plus C. There's more growth and it's faster on the plus C direction. And you can see that the new composition is a very different color than the original detrital core. So here's the original detrital core, and here's the overgrowth. So typically this growth happens when there's some sort of episodic release of boron to the system. And with continued heating and continued breakdown of other boron-bearing minerals like clays or micas in the rock, tourmaline will continue to grow, so that you could end up in a metamorphic rock with, look, a tourmaline of almost 50 microns. And this 50 micron size has 3 distinct zones, chemical zones. The very dark kind of red-brown is our original detrital core. Then you see this first overgrowth, which has a lot of quartz inclusions. It's smaller at the minus C, it's bigger at the plus C, so we'll label that number 1. And then number 2 is this broad kind of blue-green area, again, larger in this direction than in that direction, and then it's surrounded by this olive green rim. If we look at the chemistry of the tourmaline and compare the plus and the minus C directions, this isn't important. It just happens to be that this arrow plots the composition at plus C, and this arrow plots the composition at minus C. And you can see there's a distinct difference between plus and minus C in composition. If you go to the next zone, the blue zone, it now changes direction. It becomes more magnesium rich, and more luminous, but you can see the difference between plus and minus C is less. And then if we get to the very outer rim, there's no compositional change between plus and minus C. So clearly, with temperature, there's a specific type of element partitioning that gets smaller and smaller as the temperature increases. And we can use this partitioning of elements between plus and minus C to make a thermometer. So this has been quantitatively calibrated. Here's another picture of a tourmaline. And this is just a composition versus temperature plot. At the very low temperatures, there's a large difference between the two ends of the tourmaline crystal. And as it continues to heat, when it reaches about 600 degrees, there's no longer any compositional difference. So we can measure the two ends of the crystal and determine the temperature. And this has been done for two specific areas shown here. We have an area in Massachusetts where the tourmaline grew at about 400 degrees, then it was buried up to a peak temperature of about 500 degrees, and then it continued to grow on cooling. So this suggests then that this package of rocks was buried to a depth about here, at a temperature of about 550, and then rapidly uplifted. And that's a very different geologic history than what we see in the Tauern window in the Austrian Alps. So in this case, tourmaline grew at about 350 degrees, then a very episodic change happened. It was rapidly buried, continued to heat, and then it again heated and stopped growing at about 450 degrees. So this example basically tracks the fact of continental collision, and one tectonic plate was being thrust over the other during the making of the Austrian Alps. And so these are recorded in the tourmaline crystals. A second example is tourmaline as a host rock indicator. We all know zircon, right, is a great geochronometer, and it tells us the age of the rock in which it forms. Well, it doesn't tell us so much about the host rock in which it formed, but that's where tourmaline is very good. So tourmaline, again, is very responsive to its host rock environment. And by measuring only 3 chemical elements, aluminum, iron, and magnesium, and looking at those various ratios, we can plot it on this diagram, which has 8 different host rocks in which the tourmaline will form. So even when tourmaline is separated from its original rock, if we look at its chemistry, we can tell the host rock in which it came. So now we're going to venture back over to the Beartooth Mountains in western Montana, and this is part of the very old Wyoming Craton. So within the Beartooth Mountains, there is a place called the South Snowy Block, and it has the Jardine metasedimentary sequence. Very near the South Snowy Block is the Beartooth Block. It's been dated at about 2.8. So there are 4 different domains here. They're all very different in character. But this Jardine metasedimentary sequence is a steeply dipping group of metasediments interpreted to be a metaturbidite. Turbidite, sorry. Turbidite. And then it is overlain by 2.1 million year old basalts. So we have a profound unconformity here with about 2.8 billion years of break between this rock unit and that rock unit. So let's look at more closely at the Jardine metasedimentary sequence. So here, the rocks in this sequence have been investigated and shown to be metaturbidites, palitic schists, semi-peelites, quartzites, and even some banded iron formations. And they still retain some sedimentary structures, some relic sedimentary structures. There's scour and fill, there's graded beds, there's cross beds, but there's no conglomerates and no rip-up clasts. So these have been interpreted to be basically low-velocity turbidites that likely formed mid to distal fan in a pretty stable margin. We know the age of, or the youngest age of the pre-metamorphic detrital material is given by the age of the youngest zircon. The youngest zircon is about 2.9 billion years, and the zircons in this package go up to about 3.6 million years. So we know that the source of these sediments is not the Beartooth Block because that's 2.8. We have further constraints on this sedimentary sequence by the cross-cutting plutonic rocks shown here. They're undeformed, they're bulbous plutons. These are perluminous and they're epizonal. So we know from this data then that from sedimentation to metamorphism, it's about 2.8 to 2.9 billion years. It's a long time. Okay? In these rocks, there are metamorphic tourmalines. And of course, they have detrital cores. Okay? So we can use our thermometer, and this is a schematic of a detrital core with its overgrowth and the rim. This is an actual detrital core, or a detrital tourmaline within the Jardine metasedimentary sequence. It has 3 specific overgrowths shown here schematically, and we can determine the temperatures of those to be about 350, 500, and 550. So the rock continued to heat for some time. But let's look more closely at these detrital cores. So the detrital, or the outer layers, actually plot in this field. Now we've just made an XY plot of the provenance diagram in tourmalines that are consistent with an aluminous rich metapelite. So the rims mimic the rock in which it now occurs. Okay? And those are the 2 different segments from the brown to the green. But let's look more at our detrital cores. So this is a gallery of the tourmalines that were extracted from the Jardine metasedimentary sequence. And we have these tourmalines with blue cores, brown cores, and these are plane polarized light, and these are backscattered electron images. And again, the detrital cores look very different from the rims. So we've analyzed 21 different detrital tourmaline cores. So these represent the original rock type in which the sediments were formed. And we can see at least 5 different host rocks that are consistent with these detrital tourmaline. And you can see they're quite a range from perluminous granitic rocks to magnesium chromium-bearing sediments. And they span this range. Each of these clusters is a group of detrital tourmaline compositions. So this allows us then to get back at the host rock, which shed tourmalines into the basement, or into the basin that was then metamorphismed to be the Jardine metasedimentary sequence. So let's remember, so the Jardine metasedimentary sequence is this low velocity turbidite. It occurs with aluminous shales as well as this clastic detrital material of tourmaline and zircon. The host is at least 5 different lithologic units that were shedding detritus into this basin that became the metasedimentary sequence. So what this tells us then is that the rocks that were exposed from 2.9 to 3.6 billion years and that were weathering away at the surface to dump sediments into this basement had to be very evolved. They were aluminous, they were granitic, and that supports the idea of early plate tectonics. So we had to have very early plate tectonics to get these evolved rocks to the surface to be able to weather off. So this would be, so tourmalines have made their contribution to supporting the early form of plate tectonics. And then very briefly in our final example, I'd like to just briefly mention tourmaline as a recorder of transient fluids. So these are some of my favorite tourmalines. They're not the kind you're going to find in many museums, although the Rice Museum did have 1 sample of fibrous tourmalines. These things that are little blonde hairs, and they really are about this thickness of your hair, about 30 microns in thickness, those are also tourmalines. They form very late in a hydrothermal event, so they're marking the end of the fluid evolution. And they often occur with ore deposits. You don't see these often if you go to a mineral show because the miners power wash the tourmalines. So they get rid of all of the fibers. So there are not very many that actually exist. So as we know, tourmaline requires boron to form, and boron's a very fluid mobile element. Excellent response. And indeed, this is a tourmaline crystal. It's about 2 meters long and about 1 meter wide, formed in a very fluid-rich environment with a lot of fluid. And that is a person for scale. It's a full-sized human. It's not a little doll. So the fluids in these rocks can be either derived internally by mineral breakdown, as we saw in our metamorphic rocks, or they can be infiltrated external to the system. This happens in a lot of pegmatites. And tourmaline is very sensitive to these fluid compositions, so it will equilibrate with whatever composition it's around. The comp shown here is just one example where the sodium concentration in tourmaline is linearly related to the sodium concentration in the fluid phase. And this is the same for several other chemical elements. So this provides us a quantitative estimate of the fluid compositions. These are some examples of fibrous tourmalines forming late in the geologic history of the event. So this is a tourmaline that's basically fibrous and it's filling a fracture. So this is a different composition of tourmaline, and this is now a fracture fill. Sometimes tourmaline has a late stage overgrowth. It has a cap, so to speak, of fibrous tourmalines that are shown here, and of course plus C. And then this example here is a beautiful pink elbaite crystal that's been replaced by these silvery fibers of tourmaline. So we're now going to look at some of these silver fibers. So if we look in thin section down a microscope at some of those silver fibers, we see what looks like this. We see several different colors, from a dark blue to a light blue to a green, and then this is our original pink host. So we're going to zoom in on this area here. So this single fiber, we can recognize 3 distinct generations of tourmaline growth, separated by periods of dissolution. So our first generation of tourmaline growth in the single fiber is this dark blue, and you can see that here. It has a composition that's about 0.23 moles per liter of sodium, so kind of low sodium. Then it dissolved, and we know that it dissolved by this very scallopy outline to it. It then regrew with a second generation of tourmaline that's slightly lighter blue. It has more sodium because more sodium was in the fluid. And then the third generation has even more sodium, and that's represented by this dark green layer. So this single fiber represents 3 periods of fluid infiltration, of destabilization of the tourmaline, growth, dissolution, growth, and dissolution. So it basically cannibalized itself to regrow to a new composition that was in equilibrium with the new fluid. And interestingly, if we look at the trends in sodium and the trends in fluorine, those mimic, this single fiber mimics the overall evolution, fluid evolution in the entire pegmatite. So it's basically self-similar. Now, because I want to end on a high note, we're going to the top of the world. Thank you. And tourmalines have even been found on the top of Mount Everest, or very near the top of Mount Everest, at the South Summit. So here's the South Summit, and in fact, here are 2 very small tourmaline crystals. They're about 50 microns in size that have been brought down from the South Summit. So here, these tourmalines record a fluid infiltration event. The coexisting micas have been dated at about 18 million years. So the tourmalines are retaining evidence of seawater infiltration along the shear zone and likely record the thrusting and the onset of the Himalayan orogeny, shown here and here. So in summary then, I hope I've shown you that tourmaline is a remarkable and unique geologic recorder. In each tourmaline, it archives information often through its entire geologic history. You can have a detrital core through numerous overgrowths and metamorphism, fracturing and infilling, and then uplift and erosion again. So now we've been able to begin to decode some of this chemical signature that we've seen in tourmalines from the original host rock composition, which allows us to source rocks and understand the evolution of continents, to understanding the thermal history and the evolution of continental margins, and also record transient fluid events, which we no longer have access to. And we can do this we've been able to map the evolution of both mountain belts as well as small pegmatites or geothermal systems as well as salt domes. And this has happened over the last about 4 billion years of Earth's history. So thank you very much for your very kind invitation and for your interest. And I want you to always know, Julian has one up here, to always keep a black tourmaline in your pocket because it will rid you of any negative thoughts. So, thank you. If anyone has questions, I'm happy to answer. If you have any questions, I'll try to answer.
Have people tried to grow tourmaline in a laboratory with a hydrothermal bomb?
Oh, yes, yes. And that's, we've been marginally successful. It's very hard. It's stable in acidic fluids, but unstable in alkaline fluids. But we have grown it, and many of those fluid composition measurements are directly because of the equilibration in the lab.
Would you please repeat the questions?
Oh, sorry. It was about, have we grown the tourmalines in labs and hydrothermal bombs or other types of laboratory experiments? And we have it. They're easier to grow at high temperatures and pressures.
So I know that a lot of these tourmaline are very small. So boron isn't always something to be in a chemical analysis of a bulk rock. So what else would you look for as kind of an indicator? Just if you need to look in deeper.
Well, this is my bias, right? The first thing I do is make a thin section of a rock, and then I would simply look for it. But you're right, boron's very hard to measure. It's not typically included. We can't. There are now some analyses through the electron microprobe that we can analyze boron, but it's pretty dicey. Fortunately, in tourmaline, there are usually always 3 borons per chemical formula unit, and so it's easy to normalize. But I would make a thin section first.
Awesome.
Why is it hard to?
Because of its neutrons. It's a neutron absorber, and it's just difficult for the typical techniques that we use.
It's a low Z number, very low Z.
Yeah, and we tend to use the electron microprobe, which doesn't do well at low Z numbers. But lithium we can do, hydrogen we can do by basically ion microprobe, and we can analyze boron by ion microprobe, but that's a bit more tricky. And we can analyze, boron isotopes by LAICPMS. Yeah.
I have a question about the Kohinoor diamond. It's supposedly blue by virtue of boron. And I'm wondering if boron has a similar effect in tourmaline.
So interestingly, it's true. Boron is found. Oh, pardon?
Repeat question.
A repeat question. The question was, boron in diamonds makes it blue. So does boron in tourmaline, I'm paraphrasing, add to the color? How am I doing?
Right, does it
Contribute to color.
With all the advantages or disadvantages there to retain it.
right? All the advantages and disadvantages. So the short answer is no in tourmaline, but in diamond, basically what happens is diamond has a band gap, the color is caused, and boron occurs in the band gap, allowing some electrons to get into the boron, to promote it from the valence band into the band gap, and that's what causes a blue color, and that's why it's a semiconductor. But in tourmaline, most of the colors are caused by crystal field transitions and molecular orbital transitions. So it really, it isn't the band gap mineral that diamond is. So diamond is actually an insulator. It has a band gap of about 5.7 EVs. And boron lessens that band gap. And so some of the valence electrons can hop in, and that's not the case in tourmaline. That make any sense?
Yes.
Okay.
I couldn't repeat it, but it made sense.
Okay, good. Yes.
Your hair-like filaments of tourmaline, would starburst tourmaline, the fibrous form of starburst, would that be equivalent to something that you would see? We have quite a bit of starburst tourmalines throughout the Cascades. I took this group before the forest fires to a location there in Opal Creek. It has them as big as a softball. So would those qualify as something similar, a hydrothermal indicator like that?
Likely. Would starburst tourmaline that are radial sprays qualify as these kinds of fibrous tourmaline? I think they're a bit coarser in aspect ratio. These are usually 100 to 1. But certainly they're likely late-stage fluids in cavities. Mm-hmm.
I don't know. Sorry, I can always ask questions. So one thing I wasn't understanding is how you're measuring the amount of growth, like time-wise, in these. What type of analysis will tell you, like how quickly or how slowly these crystals are forming?
So that was one stage that we don't actually know the time it takes. We know the temperature, we know the composition, but we don't know the time. But we do know that tourmalines can form very fast in geothermal, hydrothermal systems. But it's very difficult to get time. We're working on that now. Some of our new analyses are trying to get potassium argon dates and argon dates on tourmaline so that we can actually map out the timing. It's a great question. That would be nice. And then it's even better than zircon. Well, thank you very much for your attention.